Okay, so in this class we'll talk about wave function. Now this is something that I found scary the first time I encountered it. This is not something which we complements our common day-to-day life perception. So this was a little surprising. But anyway, now, the reduction of wave function is being done, or it's actually quantum mechanics is based on the idea of evolution of wave function, and it's being done just to make sure that few things are satisfied. That we are able to satisfy the uncertainty principle, which is sort of very much intertwined with the idea that particles have wave nature. And the way a wave function is defined is that wave function is a function. Let's talk about right now, assuming it's a wave is a function of x and t, where x is the position and t is the time. It's not really limited to x and t. Wave function is sort of a probability of finding a particle or a system in any certain state. So here what we are trying to say, let's take an example of free particle. We have a particle that is free to go anywhere. It is just free and can travel throughout the universe. So, and let's say the wave function is given as psi x over t. What does that mean? This means that, and well, when we say it can travel anywhere, it can actually travel anywhere on the x-axis, here or here, the x-axis. So the probability of finding the particle at position x after time t, at time t, is this. So this is the probability of finding the particle at time t at position x. This was due to Max Born, and there are a few things which we can understand, and that is that we know that this should be satisfied, and the reason we have constructed it like this is because if this is the probability distribution and it satisfies this, then we know, as we know, that the standard deviation of any distribution is given as x minus mu square sum of over all the points, and this is sort of a measure of the uncertainty or error in the distribution x, as we talked about the normal distribution. Similarly, we can find the error in x, sigma x, using this wave function psi square, which will be something like, we know that in this case mu will be given as minus infinity to infinity psi square x dx. This is mu. And similarly, if you put this mu here and then find sigma x, this is what you get. You can find sigma x, you can find it. Similarly, we'll learn later, but right now I'm just telling you, and just accept it for the sake of acceptance, just to understand. Momentum is defined as momentum of the particle is given as this is the momentum. And similarly, one can find the uncertainty in sigma p, and we'll always find that sigma x multiplied by sigma p is always greater than h bar over 2. So this whole construct has been done to satisfy this equation, and anyway this needs to be satisfied. And we can take one more example, like the case of spring mass system. So the spring mass system, we know that for this case energy was given as n plus half h bar omega. Now this is the energy of the states, and these n go from 0, 1, 2, 3, and so on. And this is a spring mass system, and as you can clearly see, this is traveling in the plus x and minus x direction. So it has some probability of being found in any of these x position. If it's in state 0, which means the lowest ground state, it is expressed something like this. It has some function. It is some function of x. I don't really exactly remember, but we'll talk about this later. Also, there is another function of this another function of x and so on. There's nothing scary about this right now because we are going to talk about this anyway later. But the point is simple, that your wave function can be something like this. It can be something like minus I E0 t over h bar 0. This is a wave function, as you can clearly see. It will satisfy this condition, and moreover, as you can clearly see, it will also satisfy this particular relation. But there's one relation you can one uncertainty relation you can straightforward see. You can see that now this 0 or this 0 state actually just depends on x. So this E0 energy, so psi x has a fixed energy E0. So the uncertainty in energy is in 0. Uncertainty, actually I should write it clearly. Uncertainty in E0 is 0. But no matter at what time you measure the energy of the system, where we are saying that the system lies in the 0th or ground state, then no matter when we measure it, you will always get E0, which means uncertainty in time is infinite. Sorry for my bad handwriting. Is in time is infinite. Again, you see, it satisfied uncertainty principle regarding time and energy. Now, if it's something is going beyond your understanding right now, that's all right. The basic idea was that the introduction of wave function is simply to satisfy these relations here. And then we'll talk about the mathematical framework from the following class onwards.